Hi everybody, I wanted to give you a quick summary of how partial fractions decompositions work. So there are only a few cases to have to worry about. And in your numerator for partial fractions, it doesn't really matter what's up there, except your numerator must be lower degree than your denominator. If it isn't, if your numerator has a degree that's greater than or equal to the degree of the denominator, you have to do long division first. When you do long division, it will produce a polynomial part and a remainder part, and the remainder part will be a rational function whose numerator has lower degree than the denominator. So then you can do partial fractions on the remainder part. If you do try to do partial fractions when the numerator has a greater degree or equal degree to the denominator, it will appear to work, but it will actually be wrong. So you've got to be extremely careful. This is one of the rare cases where the math doesn't tell you that you're making a mistake. So you have to be careful. All right, so partial fractions, it all depends on what exactly shows up in your denominator. And if your denominator has a linear factor, like this, and it's to the first power, and c here is any constant. So x is the variable here. So if you have a factor in your denominator that's just x minus a constant to the first power, then your partial fractions decomposition will have some unknown constant a over x minus c, and then plus any terms that you get from other factors in your denominator. So, right, this dot 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 on the left, this is just supposed to represent whatever other factors show up in your denominator. And all of these other factors will produce their own terms in the partial fractions decomposition. Okay? But this first factor in the denominator, x minus c, produces the term a over x minus c in the partial fractions decomposition. Okay. The next possibility in your denominator is you might have x minus c but to some power, so maybe third power, and then possibly other factors in the denominator. So if you have a linear power, like x minus c, to a power greater than 1, so here we have it to the third power, you still get an unknown constant, a, over x minus c, but then you get another term with another unknown constant over x minus c squared, and then another term, which I guess we shouldn't call c, let's move on to capital D, over x minus c cubed, and you keep going with these larger powers until the power that you started with shows up in your denominator on your terms. Okay, so we had x minus c cubed. We just got to the x minus c cubed term. I missed my c. We just got to the x minus c cubed term, so that's when we're done with the x minus c's. And then, of course, you still have other terms depending on whatever other factors are in your denominator. Okay, so when you have an integer power of x minus c, you get one term for every power of x minus c up to the largest that appeared. Okay, so that's it for linear factors. You might also have an irreducible quadratic factor, something like x squared plus 1. Now this doesn't factor, at least not over the real numbers, so you can't split this x squared plus 1 into linear factors. So what does this x squared plus 1 produce in the partial fractions decomposition? Well, it would be nice, the denominator, as you expect, is x squared plus 1. And it would be nice if the numerator were just some constant, except it's not that simple, unfortunately. It's ax plus b. So actually you get two constants in this situation. And then, of course, plus any terms that correspond to the other factors in your denominator. So if you have an irreducible quadratic in the denominator, things get a little more complicated. It kind of makes sense that this numerator is, for your irreducible quadratic denominator, is degree 1, because it's less than the degree of the denominator. That happened in the linear factors too. This x minus c denominator, its numerator has degree less than that. So it kind of makes sense that you get an x here. Okay, the final possibility is that you end up with an irreducible quadratic, like x squared plus 1, to a larger power, so say squared. Let me see if I can get my brush size back down to where it was. So, and of course you might have other factors in your denominator. In this situation, you end up with ax plus b over x squared plus 1 again, and dx plus e over x squared plus 1 squared. And then, of course, plus any terms coming from the other factors in your denominator. Okay, so these are really the only 4 cases for what can happen. You might ask, well, what happens if there are factors in your denominator that aren't linear or quadratic? For example, what if you have a cubic in your denominator? Well, it turns out polynomials of degree larger than 2 always factor. So if you factor completely, you will only have these 4 possibilities: a linear, possibly to a power, or a quadratic, irreducible quadratic, possibly to a power. And the key thing that makes all of this nice is each of these situations we are able to integrate. And I will explain how that works in the next video.